All this, the absolute essentials, and that's what I mean. So I'm really going to say only what we need for the following lecture. And you might have heard this, or well, you should have heard much of this before. So take it as a reminder. So, we will need the notion of a random variable. And since we talk about different kinds of entities, we should, to be more technically correct, talk about a random element. And a random element is a deterministic function. That's why the name is a little bit infelicitous. So it's a deterministic function defined on an event space. And it is a function that depends on the outcome of a random experiment. A random experiment is defined as an experiment that has different outcomes under identical experimental conditions. So think of it as a fair, or if that exists, of a truly random one-arm bandit. So you know each time you pull the lever, you get out a different combination of symbols, or dice or roulette. Those are the prototypical examples of random experiments. And depending on the outcome of such a random experiment, it yields one of the following. It could either give a real number, and this is strictly speaking the case in which we can talk about a random variable, or RV for short, or it can give us a vector of numbers. This would be a random vector or a multivariate random variable. Or it could be a whole set of numbers that are indexed by time or by space. So this is an important instrument in the study of communication systems, for example. This is called a stochastic process. So let's say we have time, and then some process. Some people, for instance, take stock courses and try and understand these in the context of stochastic processes, and try and come up with predictors, all of which fail, by the way, on stock market. So stocks are notoriously difficult to predict. But the point is that this whole curve here is that I've shown is a single realization of a stochastic process. So I'm not just when I say stochastic process, I'm not just talking about a single number, but about a whole curve or whole function at once. Or it could be a set of numbers indexed by more than one spatial coordinate. in which case we talk about a random field. And I'm mentioning this here because much of the more theoretical work in image processing is formulated in terms of random fields. But we can think of other entities. We can think of generating random trees, random graphs, and so on. So all of these beasts are summarized under the term random element, but really in the literature people mostly talk about the random variable. Now such random variables are usually represented by uppercase symbols. To distinguish them from their realizations. So a realization, or sometimes also called the random variance, are usually indicated by lowercase symbols. And importantly, random variables induce a probability distribution on their range. I can most easily explain this by way of example. So we have discrete and continuous distributions, and mixed distributions sometimes. So discrete distributions assign positive probability to at most countably many different values. And such distributions can then be summarized by a probability function or probability mass function. So probability function is sometimes abbreviated as PF, or probability mass function PMF. So I'm going to give an example. These introductory examples are always to do with decks of cards or dice or roulette, so this is no exception. So let's consider the number of heads that are found in 3 coin tosses. This is our random variable, which I indicate with an uppercase symbol x. And then I can ask, for example, for the probability of finding 2 heads when I throw a coin 3 times. So formally, I would write what is the probability of a set of events for which it is true that the number of heads is 2, or to do this more explicitly, this is the following set. It can be head, T is what? Tail? Anna? I think. So what is the probability of this set? If I throw a coin which has two possible outcomes 3 times, I have 2 to the 3 or 8 possibilities, and 3 of these are favorable. So this probability is 3/8. Or I can write this whole thing in shorthand notation. I can say that the probability that my random variable x takes on the value 2 or has the realization 2 is just 3/8. And an even shorter notation is to just write a small p of 2. Okay, this is of course what we're going to use from now on. So I can do that not just for 2, but for, well, all possible events or number of heads that I can possibly get, and 3 coin tosses would be 0, 1, 2, or 3. We just computed the probability of finding 2 heads, and we found that the probability was 3/8. The probability of 1 head, if you look at this by symmetry, it's also 3/8. And the probability of finding no head at all or only heads is 1 favorable case out of 8, so it's 1/8. So what you see here, these 4 bars, these are my probability mass function p of x. So probability mass function p of xi is given by the probability that the random variable takes on this particular value here, and it's normalized. So the certain event has a probability of 1. I must have one of these possible numbers of heads. So the sum over these is 1. So this is a discrete random variable, and I will show you a few in pictures, and there will be much more to say about these in the future. For example, we will in the future talk about the binomial that gives you the number of successes in a certain number of trials. So you see we have 2 parameters, the number of trials and the probability of success. And if the probability of success is somewhere around 1/2, this looks pretty much Gaussian. But then if you get more extreme probabilities of success, you get asymmetric distributions. Or one that's very important for physics is the Proximal Distribution. I here show 2 different parameterizations. So this gives you the number of expected counts for certain stochastic processes, so such as photon fluxes and so on. Now this was the discrete case. We have a continuous analogon. So a continuous distribution is characterized by a probability density function or PDF for short. Such that the probability of having a random variable being inside an interval or in higher dimensional spaces in some part of the domain A, given by the integral over this probability density function, integral over this same subset. So, for example, if we take the real line as a range, we can write the probability of x being larger than a and less than or equal to b is just the integral from a to b over this probability density function. And again, this whole thing must integrate to 1. Now there's a technical point here, namely, if we have such a continuous distribution, the probability of our random variable taking on a specific value, so this is some number that's 0, even though it is not impossible to observe this value. This has to do with us having more than a countable number of elements in our range. So the observation of this value A is still possible if the probability density function at that location A is greater than 0. Okay, well, and you all know continuous distributions. The most famous one are, for instance, the uniform or the Gaussian distribution. One that we will talk about a lot is the Metre distribution. This is a distribution defined on 0, 1. It has 2 parameters, and for different values of these parameters it can have an interesting, or it can model an interesting variety of shapes. So for instance, for parameter 1/2, 1/2, we see this bimodal distribution, and actually this goes to infinity here. If we insert parameters 1, 1, we get a uniform distribution here on this interval from 0 to 1. And then as we go to larger values, we eventually get Gaussian type behavior, which, however, it will still be asymmetric if you move closer, if the parameters have different values and you move closer to either 0 or 1. So the expectation value of this distribution is given by one parameter divided by the sum of both parameters. Again, this is just for you to look at for now. We will discuss it in much more detail later, and the reason is that we can conveniently model probabilities using this distribution here. The higher dimensional generalization of the distribution is the Dirichlet distribution. So in this case, so this is for random variables that obey a sum constraint. So in this case we have 3 variables, but they must sum to 1. And for different parameterizations you get these different PDFs shown here. And the and just to drop these terms for now, and I'm going to explain them in more detail in the future, is there is a special relation between some distributions. So, for instance, the binomial and the beta, they are dual in some well-defined sense. Or the Dirichlet and the multinomial distribution are also dual. So they are conjugate to each other. And this property makes for very convenient numerics, and this is why we will have much more to say about them in the future. For now, however, we stick with the simple stuff. One of these simple things that we need is the notion of expectation and variance. So expectation characterizes the location of a distribution. It's defined as follows, and you will have seen this 100 times, I think. So in the discrete case, we sum over all of these at most countably many values in the range that are possible. So this is a small letter, this is a large letter, this is a small letter. Small, small, large. Okay, just to make the distinction between a random variable and its realization. And in the continuous case, so this equality holds if we're looking at a discrete random variable. If we're looking at a continuous random variable, we have an integral instead of the summation. Okay, and intuitively, this gives you the center of mass of a probability mass function or probability density function. So it tells you, it's also called the first moment, it tells you where a distribution lies. The next higher moment is given by the variance. Which characterizes the spread of a distribution. So it's defined as the expectation of the square of the deviation of the random variable from its mean or from its expectation, and the variance is the square of the standard deviation. Okay, and this is something that we will need in a few minutes. Okay, so the expectation tells us where a distribution lies, the variance tells us how broad it is, and then there are higher order moments which you can use to give more details about a distribution if you like. It's distributions are sometimes characterized in the Fourier domain by their characteristic functions, and you can show that if you give all the moments, then you will, for a wide family of distributions, tell everything there is to say. However, unfortunately, even the variance not always exists. So there are some distributions with very heavy tails which do not even have a finite variance. Okay, so this you will definitely have seen. Now maybe there's something new, namely, if we now start looking at distributions that are depend on more than one random variable. So we can look at so-called bivariate, if it's two random variables, or more generally, multivariate distributions. Let me start by showing a picture. So I here show a couple of things, namely unfortunately in the same color, but anyway, these are two random variables, or the possible realizations that two random variables can take, and what looks like skyscraper somewhere downtown New York. These are for this discrete bivariate distribution, the probabilities or the probability mass that you have for each of these combinations. So before I drew this picture myself, I was looking for a picture on the web, and I found one where people plot the cumulative distribution of sheep as a function of fractal dimension and time interval. I have no idea what this, why, but but it makes the point of allowing to represent here in a joint form, and this is why it's called the joint distribution, the probability of having, for instance, a fractal dimension of 1.3 at time interval t5. So if we can just look up at the corresponding position, what is the probability of having these two things happen simultaneously? So this is a joint distribution, or in German also called die gemeinsame Verteilung. This is the clean one. So what we see here is the joint distribution. Now we can, to take this example, here we had time, and here we had, let's say, a fractal dimension, just as a random example. Now I can ask, what is the distribution as sheep as a function of time, ignoring the fractal dimension? So I'm only interested in a function that depends, on one of the random variables, but not on the other. And well, one way of obtaining the so-called marginal, or Randverteilung in German, is by integrating out the redundant dimension. Okay, so if I'm integrating, or if I'm adding up all the probabilities that I find across this row, I come up with this number here. Okay, so this would be a marginal, and that would be another marginal. So this marginal on the left-hand side gives me the probability of sheep as a function of time, and this marginal gives me the number of sheep as a function of the fractal dimension, disregarding time. Okay, so we have the joint, we have the two marginals. The remaining thing that we need is a conditional distribution. So what if I can, for instance, ask the question about the distribution in time only of those sheep that have a fractal dimension of 1.1. Okay, so let's say this is all the sheep that have a fractal dimension of 1.1. So if I plot this function here, that would be the conditional distribution up to a normalization factor that I need, because once I have fixed the fractal dimension, all the sheep should add up to 100% or to 1. Okay, so I need to introduce in the conditional this normalization factor. So the conditional would be something like this here. This would be a conditional. And of course we have many different conditionals that we can define here, but only two marginals for these two random variables. Okay, now the same in formula. The joint distribution can be defined in the discrete and the continuous case as follows. In the discrete case, we ask for the probability that the random variable x has realization x and random variable y has realization y. And the shorthand notation for this is p, now this is small p, the probability mass function of x and y. And this probability mass function cannot be negative, and it should sum up to 1. So if I take, we had these funny random processes, so if I take a sheep with any fractal dimension, a random sheep with any fractal dimension any time, I must find it certainly, so it will have a probability of 1. In the continuous case, we have that the probability of a tuple xy of random variables lying in some subset of the range is the integral over the same subset I've used a small p again, but this time it's not a probability mass function, but a probability density function, because we're looking at a continuous random variable here. And again, we require normalization. It must integrate to 1. Okay, so this was the joint. Then we have the marginal distribution, again in the two cases, discrete and continuous. The probability that random variable x takes a value x irrespective of the values of y is given by summing out all the possible values of y. And that is written in shorthand notation as P of x. And sometimes, if you like, you can add explicitly the random variable, so here a capital X, to indicate what probability mass function we are talking about. Similarly, in the continuous case, the probability is given by integrating out one of the two random variables out of this joint distribution. And the probability, so again, in the shorthand notation, this looks the same. And the probability that x lies in some interval is then given by the integral over this interval. Just for my own personal statistics, who knew the marginal before? Okay, so and then we have the conditional. Again, in the discrete and continuous case. So the conditional is written as follows, or in words, the probability of x given y. So this is pronounced as given. So we know that y takes this value small y. We know that, or we fix the fractal dimension, for instance, to some value 1.3. And given this fixing, we want to know what is the distribution of sheep then over time. Okay, and that is defined as the joint divided by normalization factor. Or again, shorter, we can write this in terms of a probability mass function. So the notation here is a frequent source of error, so having a comma means joint, having a vertical bar means conditioning on, and if your handwriting is sloppy, you might, and you have a longer formula to derive, you might get mixed up between these two. We can look at the normalization here. Just to check that this division here with the denominator makes sense. So we can look at we have this conditional of x given y, and now sum over all possible values x. And by using the definition here, we had 1 over p of y times And this is the definition of the marginal. So we have P of y divided by P of y, which is 1, as desired. And then in the continuous case, the probability density function looks just the same. It's like, I can copy this formula here. Just a normalization. Looks a little bit different. So here we have the integral being 1. Okay, and that finally permits us to formulate Bayes' theorem. The first time I put a box on this board because this is important. We can write the joint in two ways. So the joint of x and y, I can either write as the condition of x given y times p of y, or I could write it the other way around. And that allows me to re-express this conditional. Okay, that is Bayes' theorem. It is fair to say that this has revolutionized the way statistics is done, and it's so important that the individual terms have names of their own. So P of y is also called the prior. So this is the prior probability of y if we know nothing yet about x. Then we have this conditional of x given y, which is called the likelihood. And together with the total probability of x, or in our sometimes called the evidence, this can be used to compute the posterior. So if you read any text about machine learning, there's always a lot of talk about posterior probability. So here it is at last. So more specifically, if we want to discuss classification, we can look at the following case. For classification, so if you want to express classification using a generative classifier, we would say that we take x as an abbreviation for the features and y as a symbol for the labels, and then p of y is the prior probability of a class. So again, in the case of predicting if a patient has tumor or not, before I have made any measurement on the patient, I know perhaps that 1% of the people who come to see this clinic will have a cancer. So in that case, the probability, without even looking at the patient, the prior probability of there being tumor would be 1%. Then we have the likelihood. So P of x given y in a classification setting is also called the class density. So this means assuming that the patient is healthy, how likely is it that we would observe the particular set of measurements that we have performed on the patient? So let's say this is feature space. We have two features, x1 and x2. And then we have those two classes. We have the healthy class. Let's say this is class 1. And then we have the tumorous class. And to really show these class densities, I could now, for instance, resort to plotting isocontours. Okay, so to give a two-dimensional depiction of these densities here. And these pictures that I've drawn here, so how likely it is, given that somebody is healthy, to observe this or that combination of two measurements. This is encapsulated by this class density P of x given y. Then we have P of x, which can be computed as a marginal. So I can sum over this is the joint, and by now integrating out y, if it's a continuous distribution, I can obtain this evidence here, the probability of having x at all. And then finally we get the posterior. So the posterior would be the probability of observing a given class, or the probability in this example that I've made, the probability of the patient being healthy or not, given our prior belief about how likely it is that he's healthy or not, and given our measurements x, so updated by our observations. Okay, so P of x would be, to put this in words, this would be the total density. So this would be the probability of observing a point somewhere in feature space, irrespective of what class that point belongs to. Okay, so this is Bayes' theorem in general, and this is how it can be mapped to the classification problem. Okay, any questions? It's very quiet. I take it that everything was totally obvious until we came to the marginals, because you had seen that before. Do you have any questions for this last part here? Maybe there is no question, because so far these are just formula. So you can say there's not much to understand. This was just rearranging stuff. So I will print some handouts in the break, and then we can look at a more concrete example to get an intuitive notion of that. And afterwards, we finally have collected all the tools that we need to approach classification in a more principled fashion than we did when we looked at the k-nearest neighbor classifier. So then we're finally equipped to look at statistical decision theory, which will tell us what the best possible classifier is and how good that can be after the break.